네, 그러면 뭐 시작할까요? 네, 이 과목을 네 번째 이제 가르치는데, 네, 되게 요번 1학년은 좀 뭔가 조용한 것 같네요. 서로도 별로 좀 친할 기회가 없었나. 네, 그래서 나는 지금 이제 전산수학 1 요 과목, 그리고 요거가 이제 어떤 내용을 배우냐면 요 리니어 엘지브라라는 과목을 이제 배우고, 네, 요 과목을 가르치게 된 이제 주재걸 교수라고 하고요. 일단 요 과목은 이제 영어 강의예요. 그래서 네, 아마도 이제 그 랜덤하게 뭔가 배정이 됐을 걸로 알고 있는데, 이게 분반이 아마 2개가 더 열리나 그럴 거예요 아마. 그래서 네, 혹시 영강보다 이제 국강을 더 선호하면 아마 다른 쪽으로 이제 그 정정 기간 때 이제 변경도 아마 가능하지 않을까 싶고, 이제 다른 쪽에 또 랜덤하게 또 뭐 외국인 학생이나 혹은 뭐 영어 강의를 더 선호하는 학생들이 있으면 이제 네, 이쪽으로 또 옮길 수 있도록 이야기를 또 해주면 좋을 것 같고요. 네, 그래서 Okay, so I'll speak in English from now on. So here's my brief intro. Okay, so I'm an assistant professor in computer science department, and I did a bachelor in electrical engineering in Seoul National University, and then did a master and PhD in Georgia Tech in the US. And then, my main research is this machine learning and interactive visualization, and then combining them together for effective use from the human's perspective. And then, this is about the brief intro about our course. So we will meet 2 times per week here in this place on Tuesday and Thursday. From 10:30 to 11:45 a.m. Okay, and then my room is currently in a science library building, which is just right next to this building. But I'll probably move soon to this building, maybe in a week. So the room number might change. Okay, and then so this is a kind of official office hour, but if you want to talk to me or discuss something with me, and then feel free to let me know after the class, or send me an email. Okay, and then so for the course material and the homework postings and submissions, we will use the system called Blackboard. Have you logged in to this website? Okay, so in this website, I already posted this course intro and maybe 2 of our first lecture materials or the slides. Okay, and then this course will mainly study the linear algebra. And then linear algebra is really a key technique in the emerging areas such as artificial intelligence or machine learning and the statistics and so on. So this is really a core and basic course for many of the other interesting areas in the computer science. So I hope you guys to take seriously this course, and then study as much as possible from this class. So this is our textbook. So it's called Linear Algebra and its Applications, and it's the 5th edition. I believe this is currently in stock in the library in this school. And then this is a English book, but also I believe it's a translated version into Korean is also available. So you can maybe purchase the Korean book as well. But please make sure to have this 5th edition instead of a 4th edition, because the homework problems that I will give you might be a little different from between the 4th and the 5th edition. then these are some course schedules. And then we will change a little bit of orders from the book, in our class. So so after studying chapter 1 and 2, and then we will jump to chapter 6, and then coming back to chapter 5, and then maybe a little bit of chapter 7. And then during our class, there is some self-study kind of thing. So, so this determinant, this topic of the determinant, I ask you to study this video lectures, given by the professor, famous professor in MIT, and then this is maybe around 3 hours long, which is composed of 2 lectures. In total it's 3 hours. So at some point I will give you this as an homework so that you can watch it, and then maybe we may have some brief quiz session after taking this video lectures. And then so we have other just typical style of a homework, such as a kind of problem solving. So I will give a list of homework problems, which is just an exercise problems in the book or our textbook, and then you just write it by your hand, or you can just type by using computers and then submit it electronically. Okay, and then we have around 5 or 6 homeworks, and then also we have 1 midterm and 1 final. This is I believe this until last year I had 2 midterm exam and then 1 final exam. So in total I had 3 exams, but from this semester I decided to have just only 1 midterm exam. So let's see if that gives a good result or not. I mean, in terms of your overall achievements in the class. Okay, and then there is a class participation which takes about 5% out of the 100% grading amount. So this is really, so don't take it, don't underestimate this part, because many of the students are placed at the borderline between the different grades, between A plus or A and then a B plus and so on. So this really changes those final gradings of many students between the around this borderline. So I strongly encourage you to just stop me anytime during our class, and then ask me any questions. Okay, and then not every time, but I'll often check the attendance. And then already counting the above 3, it will take 100%. So if you miss 1 class, and then if you had a perfect score of 100, and then you will be deducted by the amount of 0.5% per each missing class. So and then I will use so I will just check some subset of the students for this attendance, and then once some of the students are found to miss the class previously, and then I will give higher weight for those students to be selected for this attendance checking in the next or the future class. So if you miss 1 class, and then you will be checked more frequently, and then so that way you may get higher ratings on being checked for this attendance. Any questions so far? Okay, so let's start our main lectures. Okay, so we start with studying this linear equations and linear systems, or systems of linear equations. Okay, and then let me start with the really simple notion of this linear equation. So linear equation is probably what you've already handled in your middle or high school, or even in the elementary school maybe. And so it's something like this. 3x plus 5y equals 2. Okay, or maybe 3x equals 5. So this kind of questions are called linear equations. And then what is a non-linear equation? Yeah, it can be, for example, x squared plus 2x maybe minus 3 equals 0. So in this case, it's not called a linear equation because it involves this kind of second order term. Okay, so in this equation, which means we have to make the left and right part to be the same, but all the terms involved in this equation should have at least and most just one order, first order term. Okay. So in this case, we have this two variable x and y, and then it has all the order of 1. So that's why we call it as a linear equation. And then what about this? 3x plus 4xy minus y equals maybe 5. So in this case, is it called a linear or not non-linear equation? It's non-linear equation because so we basically count the number of variables that are multiplied together for each term. So for these terms, so this in total has one as a degree or the order, but in this case we have one variable which has the count of 1 as an order or the degree, and then this one also has 1 as another degree, and thus in total it is multiplied together. So it is a second order term, so it is not a linear equation. Okay, and then in these equations there are two types of numbers or elements. So in these cases, those x and y's are called our unknown or variables that I already used as the term. And also we have those numbers, right? So these numbers are called, when they are especially multiplied with our variables, and then they are called coefficients. Okay, and this one is just a constant number. Okay, so so what is what is this coefficient called in Korean? 네, 계수죠. Okay, so let's generalize it into this form. So suppose we have n different variables. So we can of course use x, y, z, w, v, and so on, but we only have like 26 alphabet letters, so we may easily run out because in advanced linear equations or maybe machine learning or artificial intelligence problems that uses this linear equations mainly, that usually deals with hundreds of thousands of variables as well as their coefficients. Okay, so we can just enumerate those variables as x1, x2 through xn. Okay, these are the variables that are unknown, and then their coefficients are also given as a1 through an, and then we have another constant called b, right? So we can generalize this form of this linear equation into this form, and then b and the coefficient a1 through an are real or complex numbers, but they are known numbers. They are just fixed numbers. And then they can be, of course, real or complex numbers like 1 plus I or something like that. But in this class, we don't usually deal with the complex numbers. So you don't need to worry about the complex number. And we only deal with these real numbers. Okay? Okay, so that was a linear equation. And then what is a system of linear equations? Or simply linear system? It is basically a set of multiple linear equations. So we have a more than one equations. Okay, so altogether that is called a linear system or system of linear equations. Okay, so for example, something like this. So we have two linear equations, and here, usually given this set of multiple equations, what we have to do is to solve the particular x and y values that satisfies both equations, right? So this is called a linear system, and this basically this problem will be what we will study for at least maybe 2 or 3 weeks from now on. Okay, so the first 2 or 3 weeks, we will just focus on this problem and how to systematically or how to like properly solve this problem when we have a many variables or like many kind of equations. Okay, so linear system is also has a Korean name. So what is it called in Korean? 네, 연립방 정식이라고 하죠. Okay, and of course this linear system will have the solution, right? So as I mentioned, the solution is the set of those variable values, set of the values for our unknown or variables that satisfies all these given equations. So that is called a solution. Okay, and then you may already have studied that this solution may be unique or it may not be unique. So we can think about the number of possible solutions. Okay. So in this case, what is the solution for x and y? Yeah, 1, right? So this is a one solution. Okay, this is one set of solution that specifies all the given variables or unknowns, right? And then, are there any other solutions that satisfies this linear system? Probably not, right? So this is we know that this is a unique solution. So in that case, this linear system has only one solution, right? And then, what are other possibilities? So can any of these linear system have a more than one solution or less than one solution? Okay, so for example, so in this case, what would be our solution? So of course, x equals 1 and y equals 1 would be the solution. So this is one particular solution. But do we have any other solutions? Can anyone give another solution? X equals, for example, 0, and then y equals 5/3. Yeah, so in this case, so if we plug in to these two equations, and then it will satisfy both equations. So that can be also called our solution, right? So in that case, we already see another solution. So altogether this system has more than one solution. And then can we find other solutions as well? Probably yes, right? So in this case, how many solutions do we have in this case? Yeah, infinitely many solutions, right? And then, yeah, often this class of linear algebra, so we are basically studying linear algebra, and one really good trick, or yeah, one kind of a really useful skill to study this this class more easily is to be able to think about it in a geometric, or think about this kind of characteristics or relations in a some particular dimensional space. So in this case, so what I mean by that is, so we can represent these equations as some line, right? So for example, 2x plus 3y equals 5. And then in this case, (2.5), and then like this value. And then we know this equation will represent this particular line, straight line, right? So all the points, like this point, and maybe 1, 1, and then 0, 3 over this number will all be our solution, right? And then what if we have another equation? For example, for x minus y equals 3. So in this case, how can we draw the line? So yep, right. So like this line. So we have minus 3 as a y-intercept, and x as maybe like this number, right? And then it will cross or intersect at this point, and we know this a particular point that is on both of these lines is our solution, right? So in this case, we know that this corresponds to having a unique or only one solution. Okay, the count or the number of solution is 1, right? And then what about this case? If we had these two equations, and then the second equation will be exactly coinciding with the first line, right? So considering all the points that are on both of these lines will be still in this line. So all the points along this line will be our solution. So that way we know that the number of solutions will be infinitely many, right? And then, I asked another question maybe 5 minutes ago. So is there any case where we have less than one solution, which means we have zero solution or no solution at all? So in that case, we know there exists such kind of case. So we have 2x plus 3y equals 5. And then for x plus 6y equals maybe 7. Wow. Okay, so in this case, you guys know that this line will be this, and then this line will be something like this. So they are parallel to each other. So in this case, they never coincide with each other, right? So in that case, we see there is no solution at all, right? So in this linear system or 연립방 정식, so we understand three different cases are possible. So one unique solution, and then no solution at all, or infinitely many solutions. Okay? And then can we think about some other cases where we have maybe two solutions, not one solution, or not infinitely many solutions, but just having a two solution? Can we have such kind of linear system? So let me give an example that has just two solutions. Yeah. So yeah, let's think about this geometry kind of a case, or their curve, and then so if one equation is something like this, and then another equation is something like this, right? And then, for example, like this line will be like x minus 3 and x plus 1, and then this line will be y equals 1/2 times x plus maybe 3. So in this case, yeah, I mean these two curves are drawn in this in this form, and then we know the solution will be this one and this one. So in this case, we will have exactly like two solutions, and then their corresponding y values as well, because if this guy was maybe -2, and then we will have the corresponding y value as, for example, 1. And then maybe this value was 4, and then this value was maybe 5, and then -2, 1. And yeah, 4, 5 will be our two of our solution, right? So in this case, we see the number of solutions will be 2, which is not infinitely many, but still more than 1. But this class is studying the linear algebra, right? And then we can see that this kind of equation. So this is also a system of an equations, okay? But this is not a system of linear equations, because this guy is a second order equation, right? So if we allow this second or more larger orders of these equations, and then this lines will be some curved lines, right? It is possible, but if we consider only the linear equations, then all the lines that are represented by the linear equations will be just a straight line, right? Just straight line. And then if we think about these two or more straight lines, they will be coinciding at only one point, but they cannot, like, once they meet, or here, and then they will be far away from each other, right? Away from, getting away from this point, right? So it cannot be bent like this and then having another solution, right? So that way, we cannot have like maybe 2 or 3 or finite number of solutions in the case of linear systems, okay? So overall, I mean, to summarize, there are 3 possible cases of, in terms of the number of solutions. Only one or unique solution, or no solutions at all, and infinitely many solutions, okay? So these 3 cases are, the important cases that we will consider in this class. Okay, so let's get back to this slide. And so we understand what is the solution, and then now we can understand the solution set, which means, which contains all the possible solutions, okay? So in this case, we will have only one unique solution, but if we have these coinciding lines, and then our solution set that contains all the possible solutions, and then this solution set will have infinitely many elements, okay? So what is set in Korean? set. 네? 네, 집합이죠? 집합. Yeah, so this is a little bit off topic, but what is the difference between set and list? Or maybe I think it can be yeah, it can have the same meaning as an array, but what is the difference between them? Yeah, right. List as a sequence, or yeah, they are multiple elements, but their orderings matter. But in the case of set, their ordering doesn't matter. So, like, you know, this set is exactly the same as like this set, right? But in the case of an array or list, so their orders are, yeah, if the orders are different, and then they are different arrays. Okay. So, given a linear system, and then we can think of this solution set that contains all the possible solutions, and then let's think about another linear system. Okay, another linear system. So, for example, so we had x plus 2y equals 3, 2x minus y equals 1. So this is a one system. And then let's think about another system that has like this. So these two are two different linear systems, but we know that these two will have exactly the same solution set, right? So you guys know that if we just multiply by 2, and then we can simply obtain this equation, one of these different equations in the other linear system, right? So given these multiple linear systems, and then if these systems have the exact same solution set, and then those two linear systems are called equivalent. Okay, equivalent. So what is it called in Korean? 네? 상등? 네, 뭐 그런 거 있죠. 상등, 뭐 동치, 뭐 다 비슷한 얘기죠. Okay. So so you guys know that the meaning of the equivalence between the linear system. Okay, and then why do we consider this equivalent linear systems? Yeah, it is because given one linear system, we keep changing this linear systems into simpler and simpler form of a linear system so that we can easily obtain the solution. Okay, so in this case, if some of you are really smart, and then that students should be able to give the answer maybe immediately. Maybe like the solution would be this, right? But how about this? I'm going to give you another linear system of this. Okay, so this is another linear system which is a different, but in this form we can just easily see the solution, right? And so those two linear systems are equivalent. So what we will learn maybe in the next few classes will be how to change this a little bit complicated form of a linear systems into this simpler form of linear systems. Okay. And then how can we change this guy into this form? Or in other words, how do we solve this linear systems from the experiences in our middle school or high school? So there were a few different methods to solve this linear system. What were they? 네? Multiplying? Yeah, right. And then in Korean, I remember like 3 different methods of solving a linear system. Or 연립방 정식. What was that? 네. What was the other one? 네. 뭐가 있었죠? 동치법 이런 거 없었나요? 네? 치환법? Okay, maybe. I don't remember exactly either. But you guys know what these two are, right? So what about this guy? What about this guy? If we had like this equation, and then we pick up maybe one of these equations and then change it as this form. So we leave one variable on the left, and then we move all the other terms into the right, and then like this, and then we just plug this into the other equations, right? And then this first equation will now involve only one variable of an x, because we just plugged y in terms of the variable, the other variables. So we basically removed this variable y, right? And similarly, yeah, so this was called the this 대입법. And what about this 가감법? So we just consider these two equations, and then maybe pick up one particular variable to remove, and then maybe we just multiply the first equation by 2, for example, and then we obtain this equation, and then 2x minus y equals 1, and then what do? We just subtract them, and then we obtain 5y equals 5, right? So that was, yeah, that was called a 가감법, or yeah, 가감 means just adding or subtracting. And what do we add or subtract? We are just adding or subtracting between the equations, okay? And then before adding or subtracting one equations with the other, we just do some proper multiplication, so that one particular variables can be removed. So we just didn't add or multiply these two equations. Before doing so, we multiply the first equation by 2, because we want to remove this first variable by just adding or subtracting these equations, right? Okay, so that was this 가감법. And then in this class, we will just focus on this 가감법, okay? And then yeah, we will just study how to do this 가감법 more systematically when having really many number of variables and many number of equations, okay? So by systematically, I mean that we will follow a particular order of removing the variables, or maybe subtracting or adding, adding the equations, okay? So we will study those systematic orders so that we can handle really a large number of variables and equations. Okay. So that was a little bit of a preview of our class. Okay, and then getting back to this linear equation. Yeah, and linear system, we know we have a either no solution, or exactly one unique solution, or infinitely many solution, and there are no other cases, right? And then let's study another term called consistency of this linear system, or inconsistency. So given a linear system which is composed of multiple equations, so we are given a multiple equation, and then we try to find the solution that satisfies all these equations, right? And then if the linear system has the solution, okay, has at least one solution, and in that case the linear system is called a consistent. And what is the corresponding cases of having at least one solution? And that is corresponding to these two cases, either unique solution or infinitely many solution. And then the system, the solution of a system is actually actually existing. So in that case, the system is called a consistent. And then if the solution has no solution at all, and then the system is called a inconsistent. Okay, so what is this meaning of this consistent in Korean? Consistent. What is the meaning? 네? 네? 뭐 한글 번역이 뭐죠? 네. consistent. 아, 얘는 뭐 굉장히 컨시스턴트한 사람인 것 같아라고 하면 뭔가 좀 그런 거 있잖아요. 일관된 사람. 네? 좀 자기 주관이 쭉 일관되고 뭐 이런 거. 인컨시스턴트한 건 얘는 뭐 이럴 땐 이랬다가 저럴 땐 저랬다가 이런 게 이제 인컨시스턴트한 거죠. So 그래서 이제 컨시스턴트라는 거는 이제 어떤 시스템이 각 이제 이퀘이션마다 모두 다 만족을 해야 되는 어떤 솔루션을 찾아야 되는 거잖아요. 그러니까 뭔가 얘네들 하나하나 이퀘이션들이 뭔가 일관된 어떤 그러니까 모두를 다 만족하는 뭔가 일관된 어떤 솔루션이 있다라는 뜻이고 얘는 이 소리를 하고 있고 이 이퀘이션은 저 소리를 하고 있어서 당초에 얘네 둘을 다 만족을 할 수가 없어요. 그러면 이 리니어 시스템 혹은 연립방 형식이 이제 일관되지 않다 혹은 이제 인컨시스턴트하다라고 얘기를 하는 거예요. Okay, so if all these equations shares at least one common solution, and then we can just consider it as a consistent cases among all these equations because they are having a one common solution. Okay, and then now let's handle this matrix. Okay, matrix. So what is this matrix called in Korean? 네, 행렬이죠, 행렬. So in this class, this matrix is the main ingredients that we handle in this class throughout the semester. And this matrix is simply this kind of two-dimensional array or list of the numbers. Okay, so we have these two axes where all these numbers are positioned or placed. Okay, so this one is can be viewed as a two-dimensional array. Okay. Okay, and then how do we relate this matrix with our linear system? Suppose we are given these three equations in our linear system. And then we have a three variable here in this case, and then in this case I can just write it in this form, right? And then once we write our equations in this form, and then we just collect all the coefficients from each of these equations, and then just form this matrix. For example, so we have 1 here, and we have these coefficients, right? And then we just simply bring all these coefficients and then form this particular matrix. Okay, so this is called a coefficient matrix because we collected all the coefficient matrix, coefficient values. And then we can think about another matrix called augmented matrix. Okay, augmented matrix. Augmented matrix is really a simple extension from this coefficient matrix. So in these equations, the known numbers. So numbers are given in this position of coefficients, and also we are given the numbers in this constant part on the right hand side, right? So they are not associated with the variables as a product form. They are just not, given as a numbers, right? So that we can satisfy the left hand side to be the same as the right hand side numbers. Okay, and then those constant values can be also brought into our matrix. So we just simply bring all these numbers into this right side of our matrix. Okay, so that way we can form this. Okay, so this is called the augmented matrix because we augmented. So we are augmenting this coefficient by this constant, by just adding it as another column on the right, right? It's quite simple, right? Okay, and then now we can think about the size of the matrix. Okay, size of the matrix. So let's just forget about the linear system and then just consider this kind of matrix. I just gave you this matrix, and then let's think about the size of it. So what is the size of this matrix? So this has two horizontal array of numbers, right? And then three vertical array of the numbers. So this has the size of 2 by 3. Okay. Yeah, and then so this will have 3 by 2 as a matrix size, right? And then what about it? What about this case? So this one is usually considered, this one is not usually considered as a matrix. So that is called what? So this is basically a one-dimensional array of the numbers. So what is it called? 뭐라 그러죠 이거? 행렬 말고 또 뭐 있죠? 벡터? 벡터? 벡터 배웠죠? 고등학교 때 배웠죠? 벡터? 벡터 안 배웠어요? 혹시? 이게 뭐가 교과 과정이 뭐가 뭐 벡터나 뭐 이런 거 다 뭐 없앤다 그래갖고 그런 게 얼마 전에 뉴스에 났던데 혹시 배웠죠? 다? 벡터? So 그 저기 그러면 그런 거 배웠어요? 회전이동?
예전 교육 과정
코사 사코 뭐 이런 거 안 배웠어요? 안 배웠어요? 나라가 어떻게 되려니죠? 큰일이네. Okay, so yeah, this is a just basically a one-dimensional array of the numbers. So that is called a vector, right? So matrix is a two-dimensional array, and then one-dimensional array is called a vector. But we can still view it as a matrix. And then what is the size of a matrix? Something like this. It has like 3 horizontal array of the numbers, right? And then only 1 vertical array of the numbers. So 3 by 1. So we can view it as a matrix of having the size of 3 by 1. Okay? And then we can also think about this 1, 2, 3. And then this one is having the size of 1 by 3, right? And then so yeah, when calling them as a vector, we can we call the first one, this vertical one, as which vector? So that is called a sum vector, and this one has another name of something vector. 네, 행벡터, vector. So which one is a 행벡터? 밑에 거, 위에 거. 바람. Yeah, right. 행, yeah, 행, 열. What is the English name of a 행? Row, right? Row vector. And then this one is column vector. Okay. Okay, and so I also studied this linear algebra maybe in the third year in my undergrad school. Yeah, it's more than it's around 20 years ago. Yeah, and then at that time I did really bad in this course, and then somehow, I kind of came to do some major. My kind of main research areas is heavily related to this linear algebra. So I didn't expect that when I did undergrad. But anyways, at that time I was still confused which one was a column or which one is a row vectors. Okay, and so. Let's just give some example so that you can avoid this kind of confusion between columns and rows. So let's think about the column or search for this keyword of column. Yeah, so column has a meaning of this kind of pillar. Okay, pillar. 그러니까 기둥 같은 게 컬럼이에요. 네. So all this kind of pillar will be just a vertical, right? So column vector will be just a vertical vector. Okay. Okay. Okay, so now you guys know how to consider or how to view the size of the matrix, and then in a general form, if we think about this m by n matrix, okay, and then it means m is the number of rows or horizontal vectors, right? So if we consider like 5 by 2 matrices, and then we have these 5 rows, and then we have these 2 columns, right? Okay, so, and then considering this the size of the matrix in the context of coefficient matrix and augmented matrix will be really, really important. Okay, so that's why we consider this the size of the matrix in this solving a linear system. Okay, so I'm gonna give just an explanation about it anyways. So so we are interested in determining the number of solutions given our linear system, and then we usually know or we usually consider the number of variables and number of equations. Okay, so in these cases of linear system, how many variables do we have? We have 2 variables. And how many equations do we have? We have 2 equations, right? So usually, so the number of variables are some kind of freedom, or the amount of the freedom that we have, right? So we can just control or like freely change those values of variables. So we have 2 kind of controlling knob, right? And then how many constraints or how many kind of equations should we satisfy? So we have to satisfy 2 kind of different requirements or equations, right? And then we have 2 kind of degree of freedom or 2 kind of number of freedom kind of thing, and then we have 2 requirements to satisfy. So if these 2 numbers are matching, and then we usually know that the system will have only one unique solution, right? It is not always the case, right? So for example, like so even when we have like 2 different equations and 2 variables, sometimes we may have infinitely many solutions when these 2 equations are exactly coinciding with each other, and then we know there might be no solutions even when the same number of variables and equations are given, right? But usually we know the number of equations are the same as the number of variables, and then usually we will have only one solution. And then what about the other cases where we have more variables than equations? So we have maybe 3 equations and then maybe 5 variables. And then we have like more freedom than the number of requirements to satisfy, right? In that case, we usually know that the number of solutions will be what? Infinitely many, because we have like more freedom than the amount of the number of requirements to satisfy, right? And then the other cases where we have maybe 2 variables, but we have infinitely many 2 variables, and then maybe we have 5 equations, and then there are too many requirements to satisfy by using only 2 control knob or 2 like number of freedoms, right? So in this case, we usually have in that case usually we have no solutions at all, right? So that that process of comparing between the number of equations and number of variables can be translated into just comparing this m by n in our coefficient matrix. Okay. So let's look at this example. So let's just forget about the augmented matrix, but just focus on this coefficient matrix. And then, so we know these 3 rows are there in this matrix. So what is the number of rows in this linear system? It is the same as the number of equations, right? And then what about the number of columns in our matrix, which corresponds to n in m by n matrix? So in that case, it is corresponding to the number of variables, right? Okay, so I'm going to give you just like this really short and fat matrix, which is a coefficient matrix from some linear system. And in that case, you can just expect that this one will have infinitely many solution or no solution. yeah, it will have infinitely many solutions. It is not always the case, but usually it will be like that because we will have many number of variables, more number of variables than the equation, right? And then what about this? So in this case, if the coefficient matrices are like that, and then yeah, we usually have no solutions at all, right? Okay, and then maybe in the first months, over the next maybe 3-4 weeks, if we find that our our linear system has no solution, and then that will be your kind of answer for your maybe homework or exam. Okay, so it will be just enough to say that okay, so in this equation, I found that there is no solutions at all. Okay, but maybe in the last months, towards the end of the semester, and then we will learn or study how to solve this linear system where there is no solutions at all. Okay, so in that case, we consider kind of an approximate solution. And that kind of computing or solving this approximate solution. Yeah, so that is really in the heart of like many of these artificial intelligence problems or machine learning problems. Okay. So I will give you just a simple example of this solving approximately the system of linear equations in the context of maybe machine learning or artificial intelligence problems. So we want to kind of predict a person's height from a person's weight. So I give you the person's information of having the weight of maybe 70 kilograms, and then I ask you to predict that person's height. Okay. And in that case, in machine learning or artificial intelligence problems, we usually consider the training data, or we are given a set of examples. Okay, so suppose you run a hospital, for example, and then you collected a person's height and weight, okay, for maybe 100 people's height and weight information, and then maybe 70 kilograms person had maybe a height of 170 centimeter, and then maybe 85, and then 180, and then maybe 60, and then this guy was maybe 175. Okay, and then how do you predict given this data? And then your main job or your prediction task will be, okay, so I will give you the person of maybe 65 kilogram, and what will be the height? So what is your prediction in this case? Okay, so in this case, they are just converted into a set of linear systems. So how? Yes. Yeah, so let's think about this case. So 70 times maybe A plus B equals 170. So we basically consider the model or prediction model where we have like this. Y equals, so this is Y or height. Height equals weight times A plus B. We just consider this kind of linear equation. Okay, so in this case we can consider this equation from the first person example, right? Okay, and then 85 A plus B equals 180, and 60A plus B equals 175. Okay. Okay, so suddenly we see a linear system, and then how many variables here in this case? So what is the unknown? A and B. So we have two unknowns, right? And then how many equations do we have? 3, right? So probably there will be no solution that satisfies all these equations, right? So even though I haven't solved this equation exactly, but we kind of expect or guess that it's likely that this one will have no solution at all, right? And then at that moment, would you give up just solving this problem, or you can just try your best to just like best solve these equations with your best. I mean, in terms of an approximation sense. So yeah, so maybe it's like, suppose A was 2 and B was maybe 30. Okay, so let's consider one case of A and B values, and then maybe maybe 1 and B equals 95. Okay, so I gave you just the two different examples of possible solution, right? And then I got this solution by just exactly matching or satisfying this equation. But if you plug these solutions into these, and then we will see that these are not satisfied, right? And then we can think about how much it is not satisfied, right? So by that I mean is, so if we plug this in, and then 170 plus 30 will give you 200. So in this case, you would predict, given a 85 kilograms person, you would predict that person's height as 200 centimeter. Okay, so it is too much, right? And then what is the error? So that person's height was actually 180, and then you kind of overestimated by the amount of 20 centimeters, right? So that will be considered as your error, right? And then, in this case, it was perfectly satisfied. And then in the second equations, you caused like the error of 20 centimeter. And then what about this third equation? 120 plus, it is actually underestimating the person's height as 150 in this case, right? And then in this case, maybe minus 25 centimeter or something like that. And then we can altogether maybe sum these absolute difference between our prediction and the actual values. And then this guy, had maybe, let's consider the absolute value. And then this solution will have the score of minus 45, right? So this solution will have in total the amount of 45 centimeters of an error given our training data, right? And then we can also think about this case as well. So in this case, I just set it as, by satisfying the first equation, the second equation, right? So in the case of second equation, it will be perfectly matching, right? But what about the first equation? So it is 7 plus 95, and then 165, and then it had, like between these two, we had a 5 centimeters of an error. And then if we plug in this into this third equation, and then 60 plus 155, and then 20, maybe. Am I correct? Right? Okay. And then if we consider the absolute difference or absolute errors, so it is like minus 25. Yeah, let's just think about the positive values as an amount of an error. So the first solution will have in total 45 amount of an error, and then the second solution will have 25 amount of an error, right? So which one would you choose? The second one, because it gave in total the smaller amount of an error, right? So in that case, I only consider these two different cases, and then what will be your best value of an A and B that will minimize that kind of an error, okay? So I just considered two specific cases, but what if we consider all the possible cases, and can we obtain the best solution that has the best error value or the minimum error value, right? So that way we can kind of solve these equations approximately, and that solution can be actually used very, very usefully for predicting these unseen data and their prediction of an height, okay? So if we simply change your data, and then it can be like height, so in this case, we are only giving one particular type of an information of an weight, okay? But we can think of the person's information, the collected person's information as maybe height, weight, and maybe blood type, and age, and the location of your residence, where you are living, right? All these information are working or playing a role of a particular variable, and then we will have a multiple variable. And then in this case, we only collected 3 people, right? So what if we collected maybe millions of people, and then we consider the millions of equations, right? And in that case, how can we solve this problem with the best approximation? And then also, if we change the target variable, so in this case, we are just predicting a person's height, right? And then let's just simply change that value as maybe a person's life expectancy. So how long will you live? Okay, how long will you live? Right? In that case, suddenly this prediction problem has really an importance, right? Because it will predict how long you will live, right? Based on your kind of input information, right? And then also it can be, for example, if we change or replace this variable with some of maybe whether you will have a particular disease, whether you will have a diabetes. 다이어비티스가 뭐죠? 다이어비티스, 당뇨병. 뭐 이렇게 몸무게, 키 뭐 이런 거 쫙 주면 당신은 이제 당뇨병 걸릴 확률이 뭐 95%입니다. 뭐 이런 거 있잖아요. And in that case, in our example, okay, so in this case of person, this person had a disease of diabetes, and then we represent it as 1. And then if a particular person had no diabetes, and then we can represent it as 0, right? Just simply 1 meaning having a diabetes, and 0 corresponding to non-diabetes. And then simply we can formulate all these interesting prediction problems or machine learning problems as this kind of linear systems. Okay. So that way, this kind of thing that we learn is really, really important. Okay, so towards the end of the class, so we will study how to approximately solve or how to obtain or compute the best solution in terms of this minimization of the total errors. Okay, so it's maybe 3 minutes or 4 minutes left, and since it's the first class, so I'm going to give you a little bit more break. So let's stop here and then continue this Thursday at 10:30. Thank you very much.